So good morning or good afternoon, everybody. The paper I'm presenting is entitled Tortuous Pore Structure of GGBFS and Limestone Powder Blended Concrete, described by multi-cycle mercury intrusion porosimetry. My co-authors are Natalia Alderete and Nele De Belli, and this work was performed at the Manuel van de Pitel laboratory from Kent University in collaboration with LEMIT. I assume most of you are familiar with the principles of MIP, which is based on the non-wetting nature of mercury, meaning it requires an external pressure to penetrate into the pore structure. The interpretation of results is generally made by considering the cylindrical shape pore model, on which the Washburn equation is based, and this equation allows to use the applied pressure to compute the pore size distribution, pore entry size distribution, by considering the contact angle and the surface tension of mercury. So we should be aware and pay attention to the limitations and simplifications of the technique, not only the use of this simplified cylindrical shape pore model, but also the potential damage caused by the maximum pressure applied and the preconditioning of drying on the structure. So the maximum volume of mercury is accountable for the accessible porosity, but the pressure itself, the values of pressure itself, correspond to the pore throat size, and only the pore entry size distribution can be defined with this technique. Usually only one cycle of mercury intrusion porosimetry is applied. We have the intrusion hemicycle, and after we reach the maximum pressure, all the cavities inside the samples are filled with mercury, and then we start the extrusion by reducing the pressure until the zero value of pressure. But at this point, some mercury will remain trapped in the cavities of the material, and this is an irreversible process. So that's why we will have a difference between the two branches of intrusion and extrusion corresponding to the volume of mercury that is permanently trapped in the material. So we can make some interpretations of the results of MIP concerning tortuosity of the pore structure. MIP itself does not analyze any transport property in the material during the intrusion, but by increasing the pressure, we connect cavities in the material through finer and finer pores, and in this sense we can analyze how the increase in pressure can reduce tortuosity by interconnecting pores in the material. So in this sense, we can analyze tortuosity with the application of MIP. So we studied concrete samples made with OPC, GGBFS, and limestone powder. We made reference samples with OPC only. The main water to binder ratio was 0.40, but for these reference samples, we also use 0.35 and 0.45 of water to binder ratio. And then we made concrete with 35% of GGBFS respective to the binder content, limestone powder 25%, and a ternary mix with GGBFS and limestone powder. With all these concretes, we cast prisms that were cured in a wet room for 28 days, and then we aged them for 2 years in the laboratory environment at 75% relative humidity, and a temperature ranging between 15 and 30 Celsius degrees. All the samples for MIP were taken from the cores of the specimens, meaning all these samples were uncarbonated. So here we have an example for the cumulative curves for multi-cycle MIP. This is for N45, concrete made with OPC and 0.45 of water to binder. And we see the first cycle of intrusion that completely fills the internal porosity of the material. And the second and third cycles of intrusion do not add up any irreversible volume of intruded mercury. So each cycle was made up to 200 megapascals to avoid any significant damage of the material, and by analyzing the second and third cycles of intrusion, which demonstrated completely parallel curves, we derived that this damage was not produced. We also observed some differences between the intruding branches and the extruding branches that in the literature, the extruded branches are shown in dashed lines here, that in the literature are mostly explained not only by the entrapped mercury, but also by the different contact angle that is produced during both processes. We are not analyzing this further in the present work, and we will only analyze the intrusion branches for the analysis of the effect of GGBFS and limestone powder. So here we have the results, the derivative course for multi-cycle MIP for all the samples. And in this course, we can identify 3 parameters. The first one is, of course, the total percolated pore volume, which is the area below the curve. And in addition to that, we can also identify the threshold pore entry size, which is interpreted as the minimum size that is geometrically continuous throughout the whole sample, and the critical pore entry size, which is the maximum of these derivative curves and corresponds to the steepest slope of the cumulative intrusion curve. So comparing all the results of the curves, we didn't observe any impact of GGBFS or limestone powder on the critical pore entry size or the threshold pore entry size. We did observe a difference regarding the comparison between the reversible and irreversible intruded volumes. And for the mixes containing GGBFS and limestone powder, and especially for the ternary mix, we observe a higher participation of the reversible volume in the total intruded porosity in comparison with the unblended mixes. However, the application of the cylindrical shape pore model shows some limitations regarding the profit we can have from the multi-cycle MIP, and alternative models such as the granular model might offer additional possibilities in this regard. So if we consider, for example, an extrusion potential that needs to be counteracted during the application of pressure and an additional zinc component for the first cycle of intrusion, we might obtain additional information from the multi-cycle MIP. However, this model still has to be further developed, and we are not ready to present applications of the model for interpreting experimental data, but this hopefully will come in the future. So our conclusions are that the results from multi-cycle MIP challenges the model of cylindrical shape pores for cementitious materials, and rethinking a model, probably the granular model, might allow us to have more profit from this technique. Moreover, the derivative course for multi-cycle MIP indicates some independence of tortuosity from the relative volume of the cavities of the so-called ink bottle pores, and the reduced connectivity and increased tortuosity due to the incorporation of GGBFS and limestone powder were effectively reflected by the results of multi-cycle MIP. So finally, we want to thank our funding agencies, Research Foundation Flanders and SID for their support. And this is all. Thank you for your attention.